Today's lecture is about how to compute compressible flows that are turbulent, and we will focus on the RANS methodology, Reynolds averaged Navier-Stokes equations. So let us start with the governing equations for compressible turbulent flow. We will write the mass conservation equation in this form. Which we are familiar with from earlier. I will write it in 1D to keep things simple, and later on tell you how to extend it to 2 and 3 dimensional flows. This is the equation we know for laminar flows. When it comes to turbulent flows, every variable, every quantity is unsteady and fluctuating. We take the mean, so rho becomes rho bar, the mean density, and U becomes U tilde. So here comes 2 different kinds of averaging. Rho bar is Reynolds averaging, which is the traditional kind of averaging, and it is represented by a bar on top of any quantity. We will see that pressure also has a Reynolds averaged form. On the other side, U velocity, U VW in a general flow, and temperature has a tilde on top, which represents Favre averaging. It is a different kind of averaging where density is used to weight the averaging procedure, and it is done to account for the variation of density in a compressible flow. Let us go to the next momentum equation, which is rho bar U tilde d dt plus rho bar U tilde square dx, the flux term, convection term, and the pressure gradient term. I'm going to, for the time being, keep the viscous terms aside, and once we learn how to handle the inviscid or the convective terms, we will add the viscous fluxes to the numerical methodology. The next equation is for energy, and it has dE dt. E is with a bar, the total energy but time averaged, mean quantity, d E bar U tilde dx plus the pressure term P bar U tilde dx, and I'm going to put it equal to 0, leave out the viscous terms. Here E bar is defined as rho bar CV, specific heat at constant volume, times temperature T tilde, average temperature, plus half rho bar U tilde square, the kinetic energy, but the mean kinetic energy, plus the turbulent kinetic energy, rho bar times K. Each of these terms, these 3 terms, is the energy per unit volume, which is E bar, the total energy per unit volume, but the mean, not the fluctuation, but the mean total energy. Now we need to compute the turbulent quantities, which represents the turbulent fluctuations in the flow, and here we will adopt the K epsilon framework, for which we have an equation for K, or rho times K, time derivative. It is also in a form which is very similar to the other equations, rho bar times K times U tilde dx, and that is equal to, on the right hand side we have viscous fluxes, we will bring it in later, and we have source terms in the form of production, dissipation, and we will again denote all of them as together as SK, and look at it later on how to handle them. The last equation is for epsilon, very similar form, time derivative of rho epsilon times U tilde, x derivative, and source terms. So we have 2 extra equations Each of these are partial differential equations, what we call as transport equation or conservation equations. So in a 1D flow, we have total of 5 equations. In a 2D flow, we will have a total of 6, and in a 3D flow, we will have a total of 7 equations to solve. 2 additional equations on top of the mean mass, momentum, and energy conservation. Okay, so now we will move ahead to see how to discretize these equations and solve them. We will follow a finite volume approach, in which we write the equations in a more compact form in terms of derivative of u vector with time and a flux vector derivative with respect to x equal to a source vector, which will have the source terms for k and epsilon. U is defined as rho bar as the first entry, rho bar times u tilde for momentum, E bar for energy, rho bar k, and rho bar epsilon for the 2 turbulent quantities. And to transpose of that, U bar is capital U is a column vector. The flux vector is also a column vector, and the first entry is rho bar u tilde from the convective term in the mass conservation equation. Momentum rho bar u tilde square plus p bar. Energy, we can again in a similar way write it, EU plus PU. I'm going to save space and go to rho bar k, the k equation, which is new, times u tilde, and a similar term for epsilon equation. So we have the flux vector, and the way we compute it using in flux vector splitting approach is to evaluate the flux in terms of a Jacobian matrix times U, and the Jacobian matrix is TF d V, and let's write it again. It's df dv times dv du, that is the Jacobian matrix, and for which we define a vector of primitive variables. Here is rho, u tilde, p bar, k, and epsilon. Once again, transpose. Okay, so once we have defined the basic quantities, basic flux vector and u and v vectors, we go ahead and compute the Jacobian matrices, and I will cut short and move to the final result as the flux evaluated in terms of 2 transformation matrices, S inverse and S, and the eigenvector matrix C inverse lambda, the diagonal matrix with the eigenvalues C, S, and then times U. This is done so that we can identify the positive and negative eigenvalues and split them into 2 parts. So I'm going to denote that by U plus and minus. With U plus, we have possibly the left running or the U vector from the left, and with minus vector, minus negative eigenvalues, we have the U vector coming from the right. The eigenvalues here, if you do all the algebra, you would get as U plus A, U minus A, the regular eigenvalues of one-dimensional Euler equations. Now we have k and epsilon equations, which also show that they get convected with the flow, which is the U vector. So we have two additional eigenvalues, each is being u, a total of 5 eigenvalues. Each of these matrices are 5 by 5 matrices, and we compute all of these at the cell faces to get the flux, and then we add all the fluxes over the 4 cell faces in 2D or 6 in 3D. Okay. We will now move on to the viscous fluxes. Here again, things are start getting fairly complicated. I will write only a few of the representative terms so that you get the idea, and if required, you can actually look up reference books, textbooks, and write the whole full expressions on your own. So we look at the x momentum, because the mass conservation equation has no viscous fluxes. X momentum, Navier-Stokes equations have a viscous term of this kind. Again, we're writing it only in 1D. In 2D, it will have more sigma terms. Now, when we come to turbulent flows, we have the additional Reynolds stress. So I'm going to write that as tau xx del x. Let me remind that sigma ij is defined in terms of molecular viscosity times dui, dxj, and similar terms. Tau ij has a very analogous form where we replace mu by mu t, the eddy viscosity, and rest of the form is almost identical. The only difference now is that we have u tilde instead of u, and mu is a mean quantity, mu bar. It turns out that eddy viscosity is always a mean quantity. We don't necessarily put a bar on top of it. So let me place sigma bar, which is the mean viscous stress, and have the Reynolds stress term along with it. The energy equation has several terms. One is sigma ij ui derivative with respect to xj. This is a term which is called the viscous work. We have seen in regular Navier-Stokes equation. Now the only difference is we have sigma bar and u tilde. We have another term which is the work done by the Reynolds stresses, tau ij ui dxj. Tau ij is again a turbulent mean quantity. We generally do not put a bar on top of it. U has a tilde on top of that. Sigma has a bar. So these are summation over 9 terms, both I and j varying from 1 to 3 in a general 3-dimensional flow. Then we have the heat conduction term, which has the form conductivity times temperature derivative dt dx j. Okay, let me rewrite this. Need a bit more of space here. d dxj of conductivity times dt dxj, summation over j. T is the tilde, mean quantity. K is the conductivity of the fluid. There are ways to compute it using Prandtl number. And viscosity. Viscosity is mu bar, K is kappa is kappa bar. Now we have to add the turbulent heat transfer, the turbulent conductivity KT, and the whole thing is multiplied by the temperature gradient. So now we have for each term that from the original Navier-Stokes equation, we have an additional term The K equation, if we go to that, we will see it has a viscous term of this kind, derivative with respect to xj, molecular diffusion plus turbulent diffusion with a model parameter times dk dxj, and a similar thing for epsilon equation. And I will skip the writing to save space. If we put all of these together, we have our viscous flux vector, which is has a first term is 0 because there is no viscous term in the mass conservation equation. The momentum equation is sigma xx plus tau xx. We leave the derivative out and rest of it is in the flux vector. The energy equation has a fairly long set of terms, and I'm going to skip writing that. We have done we'll focus on the K and epsilon equations, the turbulence equations, and here we will write mu plus mu t times sigma k times d k dx. In fact, and a similar term for epsilon, the whole thing is the viscous flux vector and the transpose of that. I started out writing for 1D flow, but at some point I switched to full 3D expressions. So for 1D, I and j equal to 1. So you can work that out. Okay. Let's do the last part, which is the turbulent source terms and how to numerically handle them. One of the main terms in turbulent source is the production term in the K equation, which we denote by P sub K, and it is in 1D it is tau xx times du dx u tilde, or a general form is tau ij dui dxj, the summation of 9 terms in 3D. Tau ij is mu t times d u I dxj and similar terms. Mu t is c mu, a model constant or parameter, times rho k square over epsilon. Now the production term is like represents generation of turbulence. It is not like a flux term which acts as at the faces of a cell, finite volume cell. The source terms actually are volumetric source terms, and they are to be calculated as volume integral over the finite volume cell. And for that reason, they are actually evaluated at the cell center. So for that, we let me write that: evaluate all the source terms on and involving Reynolds stresses, eddy viscosity, and the velocity gradients. All of these are evaluated at cell centers. For quantities like eddy viscosity, it is quite simple because rho, k, and epsilon all are stored at the cell centers. For derivatives, we have to look at the neighboring cells and find the appropriate direction and derivative. It may involve coordinate transformation if the grid lines are not in the x and y directions. Usually we use central differencing to compute the derivatives that go into the production terms. Similar derivatives may appear also in the flux terms, If it is viscous fluxes, we use central differencing. If it is inviscid fluxes with a directional bias, we use upwinding. Generally, second order accurate central differencing works fairly well for the turbulent source terms. So now we have kind of covered how to handle the inviscid fluxes, viscous fluxes, and source terms, which complete the whole set of equations that we need to compute for getting solution simulating turbulent flows in compressible gases. With that, let me stop today, and we will pick it up next time.